It's funny how sometimes the most basic math ideas, the stuff we learn early on, it can actually turn out to be pretty fascinating when you dig a little deeper.
Yeah, definitely.
So today we're diving into the world of square numbers. We've got this Square Numbers Explained for Grade 6 document as a jumping off point, but we're going to see where it takes us.
Okay.
We're looking at what makes a number square and what kind of cool, maybe even hidden patterns we can find within them.
Right. Sounds good.
So first things first, what exactly is a square number? Our document says it's what you get when you multiply any whole number by itself. Like, let's say you take the number 4.
Right.
You multiply by itself. 4 times 4, you get 16.
16.
Yep, boom. 16 is a square number. See? Simple.
Simple concept, yeah. You'll also hear people say 4 squared, which is the same thing, just shorter.
Right, squared.
And the notation for that is 4 with a little 2 up top, like an exponent, you know?
Okay.
4 to the power of 2. Mathematicians love their symbols, but it all boils down to the same thing, 4 times 4.
It all comes back to that, yeah. Now, when we say whole numbers, what are we really talking about here?
So whole numbers, that's basically your counting numbers. 1, 2, 3, 4, going on forever.
Okay,
And we include 0 in there, too. No fractions, no decimals, just good old whole numbers.
got it. So no sneaky halves or anything.
Nope. You might also hear the term integers thrown around.
Right, integers.
For today, we're sticking with the non-negative ones, meaning 0 and all the positive whole numbers.
Okay, so we're keeping things positive. Makes sense. Now, can you give me some examples of these square numbers just to, make sure I'm following along?
Sure. Think of the first few whole numbers. We've got 1. 1 times 1 equals 1. So 1, that's our first square number.
1 times 1 is 1. Got it.
Then we got 2. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. And 5 times 5 gives us 25. And let's not forget about 0.
Right, 0.
0 times 0 is 0, so that makes 0 a square number, too.
Interesting. 0 sneaks in there. All right, so we've got what they are, but this word square, that has a visual side to it too, right?
Oh, absolutely. The name comes directly from the shape, a square, all sides equal.
Right, equal sides.
And to find the area of a square, you multiply the lengths of one side by itself. So you end up doing the same thing as when you calculate a square number, multiplying a number by itself.
Ah, I see, I see. So, like, if I have a square and each side is, say, 5 centimeters long,
Right.
the area would be 5 centimeters times 5 centimeters,
Exactly.
which is 25 squared centimeters. And 25, we know that's a square number.
That's it. So anytime you have a square and the sides are whole numbers, the area is always going to be a square number.
Neat. It's like geometry meeting arithmetic.
Exactly. And it gets even cooler because you can actually visualize these square numbers, like see them in your head or even arrange objects to represent them.
Okay, I'm intrigued. How so?
Think about using dot or blocks or something like that. Like imagine the square number 9.
9. Okay.
You could take 9 dots and arrange them in a perfect square, 3 rows of 3 dots each, 3 by 3 grid.
Right, 3 by 3, 9 dots total. Makes a square. I see it.
There you go. And you can do that with any square number. The square number 1 is just a single dot, a tiny little 1 by 1 square.
Right, just a dot.
The number 4, that forms a 2 by 2 arrangement. 9 is 3 by 3, 16 is 4 by 4.
So the side length of that square you make with the dots, that matches the original number you squared?
Precisely.
Like with 16 dots, the square side is 4 dots long because 4 times 4 equals 16? That's cool. It makes it way easier to picture.
It's a great way to grasp the concept visually. And speaking of visuals, our Square Numbers Explained document mentions another place where they show up visually, a multiplication chart.
Oh, right, the multiplication chart.
If you look at its standard one, the kind we all used in school,
Yep, got it.
the numbers that run diagonally from the top left corner down to the bottom right, those are all your square numbers.
Ah, because on the chart, those diagonal spots are where you multiply a number by itself.
You got it.
1 times 1, 2 times 2, 3 times 3, and so on. It's like a little hidden path of squares right there in the chart.
It is. It's a nice way to visualize the sequence of square numbers and to reinforce the idea that they come from multiplying a number by itself.
Okay, so we've covered what they are and how they look. Let's get down to the nitty-gritty. How do we actually calculate these square numbers?
Well, as we've already touched on, the main rule is you just multiply the number by itself. That's the core of it.
Multiply by itself. Got it.
The document walks us through a few examples.
Okay.
Like if you want to find 7 squared, you do 7 times 7, which equals 49.
49, right.
And for the square of 12, that's 12 times 12, which gives you 144.
All right, so it's really just knowing your multiplication facts.
Pretty much. And like anything in math, the more you practice, the easier it becomes.
Right, practice makes perfect. Or at least, better.
Exactly. The document even throws in some quick practice questions to test you.
Oh, like a pop quiz.
Kind of like what's 6 squared?
6 square. Okay, let me take 36.
You got it. And what about the square of 9?
The square of 9, that's 81.
Perfect. And how about if you calculate 8 squared?
8 squared, that's 64.
You're on a roll. It also asks things like, What number squared equals 100?
Ooh, that's 10.
Exactly. And it even repeats the question about 7 squared, just to make sure it sticks.
Reinforcement, I like it. So I'm guessing there's a point to all these practice problems, right?
Oh, definitely. Knowing those basic squares up to like 12 or so, it could be really helpful in math.
Okay, that makes sense.
You might even already know some of them from your multiplication tables.
Yeah, probably. The multiplication table's always coming back to those.
Always good foundation. And to help you memorize them, the document actually has a table listing the squares of numbers from 1 to 12.
Oh, that's handy.
It shows both the multiplication, like 3 times 3 equals 9, and also the notation, like 3 squared equals 9.
Visual and symbolic. Nice.
Exactly. It's like a cheat sheet right there in the document.
I like cheat sheets. Okay, but now this is where I think things start getting really interesting. The document goes into these secret patterns within square numbers.
Ah, yes, the patterns. Square numbers are full of them. It's like a little secret code waiting to be cracked.
I love that kind of stuff. Makes math feel more like a puzzle. So what kind of patterns are we talking about?
Well, the first one they highlight is the difference between consecutive square numbers.
Consecutive, so like one after the other.
Exactly. So let's list out the first few. 1, 4, 9, 16, 25.
1, 4, 9, 16, 25. Okay.
Now, if you look at the difference between each pair, you get 3, 5, 7, and 9.
Wait a minute. 3, 5, 7, 9. Those are all odd numbers in order to...
That's the pattern. Each time you move to the next square number, you're basically adding the next odd number in the sequence.
So to get from 25, which is 5 squared, to 36, which is 6 squared,
Right.
you add 11, which is the next odd number after 9. That's so cool. But why does that happen?
That's the million-dollar question, right? Think back to how we visualized square numbers with those dots.
Okay, the dots.
When you go from a 2 by 2 square, which is 4 dots, to a 3 by 3 square, 9 dots, what are you doing? You're adding a new row of 2 dots, a new column of 2 dots, and one extra dot to finish the corner. That's 2 plus 2 plus 1.
5, which is an odd number.
Exactly. And as you keep making bigger and bigger squares, you're always adding 2 sides in a corner.
Which will always be odd.
Always. It's not just a coincidence. It's built into how these squares grow.
That visual explanation makes it so much clearer. It's like the pattern is encoded in the shape itself. Are there any other interesting patterns with these square numbers?
Oh, there are plenty. Another that the document mentions has to do with the squares of odd numbers. It says that if you square any odd number, except for 1, the result can be written as the sum of 2 consecutive numbers.
Hold on, can you give me an example? I'm not sure I'm following.
Sure, let's take the odd number 7. 7 squared is 49.
Right, 49.
Now think about the numbers around 49. It's the same as 24 plus 25.
Wow, and those are consecutive numbers.
Exactly. Let's try another. The odd number 9. 9 squared is 81.
81, okay.
And 81 is the same as 40 plus 41. Again, 2 numbers right next to each other.
That's amazing. It's like there's this hidden structure within square numbers that links them to these consecutive number pairs. It's kind of unexpected, you know?
It is. It really shows how interconnected different parts of math are. But let me show you another cool trick the document mentions. This one's about the last digits of square numbers.
The last digits.
Yep. It's a handy shortcut for figuring out if a number could even be a perfect square.
Okay, tell me more.
So square numbers can only end in certain digits. They can end in 0, 1, 4, 5, 6, or 9.
0, 1, 4, 5, 6, or 9. Got it.
But they can never end in 2, 3, 7, or 8.
So if I see a number like, say, 73,
Right. 73 ends in a 3.
which isn't on the list, so it can't be a perfect square, that's a really useful trick.
It is. It's a quick way to eliminate possibilities, which can be super helpful in math. It's like a little filter for identifying square numbers.
I love that. All right, we've talked a lot about squaring numbers, but the document also mentions finding the square root, which is like the opposite, right?
Exactly. Finding the square root is like asking, what number, when multiplied by itself, gives me this square number? It's like going backwards from squaring.
Like undoing the process?
Exactly. And just like squaring has its own symbol, square roots have their own too, called the radical symbol.
The radical symbol? Is that the little check mark thing?
That's the one. It looks like a check mark with a line extending over the number.
Right, okay, I remember that from math class.
So when you see that symbol with, say, 16 underneath, it's asking for the square root of 16.
And since 4 squared is 16.
Exactly. The square root of 16 is 4. Same logic applies to any square number.
So the square root of 25 is 5, because 5 times 5 is 25.
You got it. And the document gives a bunch more examples. The square root of 9 is 3. The square root of 49 is 7. Square root of 100 is 10.
Okay, I'm starting to see the pattern here. Now, the document also mentions perfect squares. What makes a square perfect in this context?
A perfect square is just any number whose square root is a whole number.
Okay, so no fractions or decimals involved.
Exactly. Nice, clean whole numbers like 9, 25, 16, 100. Their square roots are 3, 5, 4, and 10. All whole numbers.
Makes sense. So for now, we're focusing on these perfect squares and their nice, easy square roots.
Right. There are, of course, square roots that aren't whole numbers, like the square root of 2, which is a decimal that goes on forever. But we could dive into those another time.
Maybe a deep dive for another day.
Exactly.
So are there more practice questions for square roots?
Oh, you bet. The document makes sure you really get it. It asks us things like, what's the square root of 36?
That's 6.
Yep. And what about the square root of 81?
Square root of 81, that's 9.
Right again. And then there are questions like, what number multiplied by itself equals 144?
That would be 12.
You're getting the hang of it. And just to reinforce it, they ask about the square root of 49 again, which we know is 7.
Repetition is key, right?
It is. And knowing your basic squares really helps with figuring out the square roots.
It's all connected. I like how the document doesn't just keep things abstract, though. It shows how square numbers actually exist in the real world.
Oh, absolutely. They're all around us. And that's one of the coolest things about math.
Totally. So where do these square numbers show up in real life?
Well, one of the most common places is in geometry when we talk about the area of a square. As we saw earlier, to find the area of a square, you square the length of one of its sides.
Right, area equals side squared.
Exactly. So imagine you're tiling a bathroom floor, and it's a perfect square, 3 meters by 3 meters.
Okay.
To figure out how many tiles you need, you'd need to know the area. So you do 3 squared, which is 9 square meters. Square numbers in action.
Makes sense. And going the other way, if I knew a square garden had an area of, say, 64 square feet,
Right.
I could find the length of one side by taking the square root of 64, which is 8 feet.
Exactly. So whether you're figuring out how much space something covers or what the dimensions of a square are, square numbers are essential.
They're super practical. And it's not just about geometry, is it?
No, not at all. Think about all the things we see every day that are arranged in squares. Tiles on a floor or a wall, they're often in square grids.
Right, tiles. I never thought about it that way.
A classic example is a chessboard. 8 squares by 8 squares, that's 64 squares total.
The chessboard, of course, a perfect example of a square number in action.
The document also mentions things like picture frames, some photos, board games that use square grids, even those building blocks kids play with.
Oh, yeah, those blocks you can stack and make towers.
Exactly. They can be arranged in squares too.
It's amazing how something so simple as a square number can be found in so many different things.
It really is. And the document even touches on connections in nature, like the spiral patterns of seeds in a sunflower.
Whoa, really?
Yeah, it turns out there are deeper mathematical relationships at play there too, but that's a whole other topic.
Maybe another deep dive.
Exactly. But before we move on to the FAQ, the document shares a few more fun facts about square numbers. Little bonus tidbits.
Okay, I'm all ears.
Well, first it reminds us about that rule with the last digits. Remember, square numbers can only end in 0, 1, 4, 5, 6, or 9.
Right, got it.
It also points out how even and odd numbers work with squares. If you square an even number, the result is always even.
Okay, even squared is even.
And if you square an odd number, the result is always odd. Like 6 squared is 36, which is even, and 5 squared is 25, which is odd.
So even stays even, odd stays odd.
Precisely. Another cool thing is about perfect squares that end in 0. They always have an even number of zeros at the end, like 10 squared is 100, 30 squared is 900.
Right, 2 zeros each time.
You'll never find a perfect square ending in just one zero, like 20 or 70.
That's a good thing to remember.
And lastly, it circles back to that pattern we talked about with the difference between consecutive square numbers. Remember how it's always an odd number?
Yeah, that was a fascinating one.
It's like a recurring theme in the world of square numbers.
I'm starting to see that there's a lot more to these seemingly simple numbers than meets the eye.
Absolutely. These extra facts just add another layer of intrigue, highlighting the structure and predictability within this seemingly simple concept. But to make sure we've covered all the bases, the document finishes with a helpful FAQ section.
FAQs, always useful. Let's go through some of the key questions and answers. So first up, what is a square number in the simplest terms?
A square number is what you get when you multiply a whole number by itself.
Straight to the point. And what are the first 5 square numbers?
Those would be 1, 4, 9, 16, and 25.
Okay, got those memorized by now. And how do you actually calculate a square number?
Simple. You multiply the number by itself.
The fundamental operation. Now, why do we call them square numbers anyway?
Because visually, that many objects can be arranged into the shape of a perfect square.
The shape is key. And reversing the process, what exactly is a square root?
The square root is the number that, when multiplied by itself, gives you the original square number. It's like finding the missing piece of the puzzle.
Ah, okay. So can square numbers ever be negative?
Nope, never. When you multiply any real number by itself, positive or negative, the result is always positive or 0. Never negative.
Always positive or 0. Got it. Now, where might we encounter square numbers in everyday life?
Oh, in so many places. Like when figuring out the area of a square space, in the patterns of tiles, on game boards like chessboards, and in tons of other structures that are based on grids.
So many examples. It's like they're everywhere. And lastly, the document briefly mentions other types of number shapes. What are those all about?
Well, just like square numbers can be visualized as squares, there are triangular numbers visualized as triangles, and cube numbers visualized as cubes. And there are even more fascinating figurate numbers that connect to various geometric shapes. It's a whole other rabbit hole to explore.
That's for sure. Another deep dive for another day, perhaps.
Def
Well, there you have it, our deep dive into the world of square numbers, all thanks to that super helpful Square Numbers Explained for Grade 6 document. It's amazing how much depth there is to this seemingly basic concept.
I agree. They're more than just a mathematical idea. They're a building block with clear visuals, cool patterns, and real-world applications that pop up everywhere.
It's like a new lens to view the world through.
Exactly.
So the next time you see a grid of anything or you're trying to figure out the area of a square, take a second to appreciate the square numbers at play. It might just make you see things a little differently, and it makes you wonder what other basic math concepts might have such hidden depths just waiting to be explored.
That's the beauty of math. There's always more to discover.
Thanks for joining us on this deep dive.
My pleasure.